Good morning again. So this is 504 Foundations of Deep Learning, and this is the final week. This week I'm going to be doing a summary of what we have been talking about, what we learned. I think it's going to be helpful to remember what we've gone over, and regarding the order that we went over these subjects, actually there is a big picture that I want you to see once again, because this big picture is the picture of the introductory level deep learning course that you've taken. And having this experience, I mean, having taken an introductory level deep learning course, now it is time to continue for you. We can discuss which direction, maybe in the end of the lecture, towards a PhD or towards a more advanced concept, towards a position in the industry. There are many directions, but this was the introductory level course. So let's begin this summary, then we'll conclude with discussions. So the title is Deep Learning. Deep Learning was a recently found subfield of machine learning and artificial intelligence. So artificial intelligence was the broader title, where it was human intelligence exhibited by machines in any means. I mean, from state vector, state machines, finite state automata, to any algorithm that you can come across that we didn't cover. And machine learning was a data-based approach within artificial intelligence. And neural networks was a method within machine learning, and deep learning was a recently grown subfield of neural networks. It definitely a specific type of neural networks, which we call deep, with many layers. You already know this. When I showed you this this slide for the first time months ago, weeks ago, you didn't know what that meant, but you now know it. Deep learning is some sort of artificial neural networks with many layers. Good. So what was machine learning? We take a step back. Machine learning is you develop computer programs based on data engineering. So machine learning uses data. And they are usually categorized according to how they are supervised for training. So you see, we have made the definition of training. I'm going to go over the details of training deep neural networks as we did before. However, in a broader sense, machine learning is about using data to train models. And when you're doing that, there are three ways you can follow: supervised learning, unsupervised learning, and reinforcement learning. We have been dealing with supervised learning in this course because this is an introductory level course. However, having taken this course, I believe that you are ready to follow different directions. For example, we have a reinforcement learning course in our department, not DI. I'm from the MMI department, you all know this. And as far as I know, it's going to be available next semester. I strongly recommend those who will be working on training systems online in environments. So the supervision will not be conducted by collected data and previously annotated data, just like in supervised learning, just like we did. It is done usually online with instructions of the agent to the environment. Or unsupervised learning, you have no idea about the data, there is no annotation, and you've just got the data. This was what we've done. How did we do it? So let's continue. So supervision in machine learning is something very important. I mean, actually, the revolution, let's call it the revolution in deep learning that happened in the last decade was for supervised machine learning. People are working on weakly supervised methods or unsupervised methods, and they are trying to find ways to make them more efficient. However, we still do not have the impact that we had with supervised learning, considering unsupervised learning and other unsupervised like learning stuff, like weak supervised learning. For example, what is weak supervised learning? You have some annotations, but they are either noisy or they are not, they are not strong enough. For example, in semantic segmentation, let's consider the semantic segmentation problem. In semantic segmentation, You need pixel-wise labeling, just like in unit. However, think that we only have box labels, like object detection annotation. We have the objects in boxes. This is not the annotation you need for semantic segmentation. However, these days, the recent papers in semantic segmentation are trying to find algorithms to use those box annotations only for semantic segmentation. So this is called weak supervision. So what we've learned in this introductory level course was supervised learning, which uses input outputs with specifically defined input-output relations to models. And I think we've learned that, but the next step is unsupervised or weakly supervised or noisy supervised learning. Okay. So this is one of the important things that we should consider about this course. This was only supervised learning, guys, but the future of deep learning is more than that. Good. So we know the definitions now. Before we get into deep learning, we talked about the workflow of general machine learning platforms, because that's all data scientists should keep in mind. That's something that's a workflow which is fundamental for any data scientist. You do data collection, you do preprocessing, and sometimes feature extraction. Remember, we talked about features being extracted by the deep learning model, which are called deep features, which I'm going to be mentioning in the following slide. But for some deep learning models, we use feature extraction as well. We talked about this. We either called it, for sound, it was extracting the spectrograms, the frequency behavior of the sound. For text, it was constructing embeddings, either by deep learning methods or by some handcrafted methods like word2vec. We've done an introduction to. Then, having this data, the input data, we train the model. And in supervised machine learning, what we did was we were trying to find parameters of the model which would match the input to the labeled output, which we call the ground truth, okay? Then after training, using the training data, we did evaluation, which was called cross-validation. We discussed this in the live code session in week 12, you remember. I'm going to get there, give it in slides, don't worry. And finally, if you are satisfied with the evaluation, testing or validation, we fine-tune the parameters so that we change the parameters a bit to give it best performing level. So this workflow is kind of the fundamental workflow in every machine learning project. And you are completing a project right now. Some of you are doing it right now. Some of you maybe already completed it, I don't know. But you must follow every step. And when I'm evaluating your projects, your reports, I will be checking these steps, guys. So what about the data collection? If the data is inherited from a website, what is the analysis of the data? What kind of preprocessing or feature extraction? If there is none, did you indicate the reasons? I mean, okay, you did not apply any preprocessing or feature extraction, but why? I mean, because if it was useless to do so, the reasons why. Then the training, then the evaluation, then the fine-tuning. I will look for every step. Just keep that in mind, okay? So we learned about features. As the features word flips, I'm sure you know where I'm trying to get to. In machine learning, feature is a very important definition. In week 2, we have discussed the feature spaces. And feature spaces was the mathematical space, mathematical coordinate system where we represented the data. So these features were like the characteristics of the data. Sometimes they represent something. It could be tangible or not. I mean, you could name it or you could not name it. But in the end, feature is a high-level representation of the data. It would represent something. Even if it doesn't represent something to you, it would represent something to the model. That's what we call feature. I mean, if it doesn't represent anything to the data, so it is like you have data to the model, I'm sorry. You have data, you transform it to a feature, and it doesn't mean anything to the model. Then that's not a good feature at all. So features are basically higher level representations of raw data. And what we call the process of extracting these features from raw data to some meaningful features, again, doesn't have to be meaningful for you, but it's going to be meaningful for the model. We call it feature engineering. And as I've mentioned a lot of times, before the era of deep learning, like which started about a decade ago, it's more than that right now. In the 2000s, this society focused mainly on feature engineering. And I always tell you, it was the times that I did my PhD. I did my PhD in 2000s. And everybody in vision society or machine learning society were doing feature engineering, guys. It was the race of engineering the best features. And I myself have an engineered feature in my PhD. But it is something good. I mean, we as the guys who have engineered features have a strong insight on data, and we can analyze the features created by deep learning models. So I think it is still not dead yet. I mean, it's still living. I mean, it's an old method. You don't need the features most probably created from handcrafted methods, but still those features correspond to things, and by the similarities that you have of those features to the deep learning features, you can get some insights. So it still counts, in my opinion, or I'm trying to make myself happy about it. I don't know. Anyways, then we discussed this deep learning versus ML features business, because that's the trademark of deep learning. That's why we have an introductory level deep learning course, and that's why it is the most popular course in this field, in informatics. Maybe, I don't know, in informatics there are many courses, but in the field of AI, introduction to deep learning is kind of the most popular course. I think you would agree on that. It's not that I'm lecturing this course. I'm not saying it that because of that, but I mean, the numbers speak. So we can safely say that, I guess. So deep learning is actually, since the trademark of deep learning is extracting these features, deep learning is the type of machine learning which progressively extracts high-level features from raw inputs. I mean, it is the way it is defined in Wikipedia. So if you ask me what deep learning is, I mean, you can say it's a bunch of artificial neural networks with many layers. That's correct. But what is the trademark of it? It is its ability to progressively extract higher level features from raw data itself, not by engineering. That's why with deep learning, the traditional machine learning flow changed. It was feature engineering, having the features, picking a model, a machine learning model, according to those features. So the selection of machine learning algorithm was handcrafted as well, and you've got the output. So it was like for pedestrian detection, you use histogram of gradients and you feed them to support vector machines. I mean, that's the accurate example. That was what everybody had done, because they tried every machine learning model with combination of any features that you can think of, and they had the results like this. For pedestrian detection in images, histogram of gradients feature with support vector machines. That was how it's done. Now it's end-to-end. This process is called end-to-end, from the input to the output. When you're doing supervised machine learning, the deep learning flow encapsulates everything at all. I mean, you have the feature extraction and everything inside. There are ways to analyze it, and we've discussed them. You remember Usinski in the previous weeks. There are ways to analyze the features that you extract from deep learning algorithms. Depends on the type of deep learning algorithm. If it's a CNN-based algorithm, it is the output of the convolutional layers, if you remember. But if it is a different type of algorithm, for example, a text-based algorithm, it is a bit different. You need mechanisms like attention that we have not covered in this course. But if you take a text analytics course, just like Tuba or just, you're going to go over them and stuff. Okay, then having learned the trademark of deep learning, we learned the statistical way of training a model before we trained the model hands-on, which was called cross-validation. Cross-validation is an important technique. Remember, and it has many misconceptions as well. I mean, remember the week that we discussed it, week 12, you had many misconceptions. I'm sorry. What you do is you have an entire set. Okay, you collected data. and you annotated the data. So it's all annotated. You want to test your model with it. You want to test, before testing it, you want to train your model. So what you basically do is, I'm going to go over it once again, although we have done it in week 12. You split it first to test and the rest. The rest is called the training usually, but validation is considered to be a part of the training because you use the validation set during training. Okay, so for example, you take the 20% of it. Okay, then you have the 80%. Then you do something like 72% to 8%, for example. I don't know. I'm just trying to find ways to make it 100% in total. So what you do is you train the model with this training set. Using the validation set, you get some results. The results of the training set and validation set will be different because the model will try to overfit to the training set, and the validation set is used to give you a sense of that overfit because you have not used the validation set during training. So for the training sets, you will have an accuracy of, for example, 87. I don't know if it is a classification task. It's multi-class classification. It's the average precision accuracy. But for the validation set, you will have 73%. So you do things, you do augmentation, you change parameters, and you try to make the validation sets up. And at some point, you say, that's enough, that's the perfect model. And then you test it with the test model and you give the results. And it will give you something like 75% for the test. And that is your result. And if you want to do this on the entire data, what you do is you pick another part of the data as test now, another 20%. And you do the rest for training and validation, and you complete this training and tuning and parameter optimization experiment once again. Since I selected it 20%, you will have to do it 5 times. And that's called 5-fold cross-validation. Okay? We've discussed this already in week 12, so I strongly recommend you refer to those discussions. It's going to help you a lot. This is the statistical true way of testing your hypothesis for an entire set. But I repeat, remember when we were discussing this cross-validation in week 12, I always said, usually in practical machine learning projects, there are some distinct training and test sets, usually in challenges, in Kaggle challenges and other challenges. You are given the training set with the annotation data if it's a supervised experiment, and you have the test set, for which you are not given the annotated data. So you train your training set, and you send your model to the challenge, I don't know, and your model is being tested for the test set only. So it is not n-fold, but that's the nature of the challenge. If you're not doing a challenge, if you have an entire set, you must do cross-validation and n-fold cross-validation. Because if you select only one part of the test set for your experiment, you will not be doing something statistically correct. Maybe the part that you've selected as a test set is a part which is easier to find for the model. Then the accuracy values you get for that fold will not be correct, will not be representing the entire problem. Okay? So that's why we do n-fold cross-validation. Good. So after learning the workflow, after learning cross-validation, we've talked about machine learning pipeline. And this is the simplest way to put it, I guess. You have training data, you do training, you have a model. With the validation data, you do parameter tuning. After you're finished with this, you have the test data, you do the prediction and the results. And you repeat this for different folds. Okay? Okay, so when we were ready with the fundamentals of machine learning, we delved into the types of problems in deep learning. I mean, in deep learning, deep learning is a mathematical input-output black box. So you can create any type of problem with it. But the problems that we come across in the literature are scrutinized into some certain titles, like detection, classification, or very similar problem recognition, localization, segmentation, regression, and generation. And actually, the things that you learn in this course covers almost all of these problems except for generation. Generation is a bit different task, which requires some different type of architectures like autoencoders or generated adversarial models, GANs. We did not cover those, but I believe they are advanced concepts, and mentioning them in an introductory level course may be okay, but covering them will not be possible. Covering them entirely, maybe. So detection was designating the existence of a type of a signal. So speech detection on a sound signal, or face detection on an image, or animal detection in a text, whatever. This is detection. Classification recognition is you have multiple classes or two classes. I don't know. We have more than one class. You are trying to classify the input data according to some categories. Localization, you have region of interest within the signal. It could be text or it could be sound, doesn't matter. You are trying to find the swear words, for example, bad language in a text. That's localization. Segmentation is you have class definitions and you're trying to find regions within the signal where you can categorize each region for a class. For an image, it is semantic segmentation, pixel-wise labeling the pixels. For text, it is trying to find, you could find different definitions for segmentation in text. For example, you could find in a book, dialogues versus narration. That would be a type of segmentation for text, for example. I'm trying to give you an example. And regression is finding a value, reconstructing a function. And that's also the capability of the deep learning models. Okay. At this point, when we talked about this, it was either week 2 or week 3. We started, it was the first time we delved into the mathematics of it. And in order to delve into the mathematics of it, we defined the so-called score function. So let's remember it. The score function is, so this model, either a deep learning model or a machine learning model, was an input-output relation, right? You have an input and you get a value out of it. Well, depending on the type of problem, this value may change. If it's a regression problem, it is just a value. You're trying to estimate the temperature of the next day. Well, that's a regression model. If you're trying to estimate the class label of the input, that's a classification problem. Whatever. You have a black box. While you're doing that, since this model is something mathematical, it's going to output a mathematical value. That mathematical value is usually called the score. This score value may not be the exact output value you are looking for, because for a classification problem, you are looking for a class category. You have some numbers for each category, for example. Number 1 is cat, number 2 is dog, kind of. But your model will most probably create a real value, because you remember these, I'm going to cover it in the following slides. The models are some weight multiplications and some real operations. So before you get to that classification value, that category index, you create a value. That's called a score. And the raw output of these models were called the scores. That's why these raw models are also called the score functions. And the values they output, the raw output, is called scores. So it is like you have an input x, you have the parameters of the model theta, and you've got the score y. Good. So why this score is important? Because in supervised learning, we are trying to create a score function which would help us to get the ground truth of that input. Okay, so if it's a cat, it's going to give me a cat. That score function should be appropriate. For that score function to be appropriate, we need these parameters to be set correctly. That's what the training was. So let's remember what ground truth was. Ground truth is basically the annotations added to it. So you, by human efforts or by different means, you create a data set where each sample in the data set, they could be images, they could be sentences, whatever, are annotated according to the problem definition. So ground truth is something correlated with the problem definition. So if you're doing a single object detection, that will require a different type of annotation. If you are doing multiple object detection, it would require a different type of annotation. If you are doing segmentation and instance segmentation, which means you are segmenting each instance of the same category differently. So there are cats. You're not saying these are cats. You're saying this is cat 1, this pixel belongs to cat 1, and this pixel belongs to cat 2. This is called instance segmentation with respect to general semantic segmentation, whatever. So you need specific type of annotations. Those annotations are called ground truths. Okay, so using the ground truth and using the score function, we understand how well the score function is doing. Okay, so you have a score function. You want to know if that score function will create this ground truth or not. So what you do is, in order to find how good this score function is doing, we define a loss function, which is a function that takes the score and the ground truth and creates a value. And usually this loss is, or it's also called cost function in optimization literature, is a value which is smaller the better. Which means if it is 0, well, you're doing perfect. If it is high, if it is positive infinity, well, you're totally not aware of what you're doing, which means the loss function is. So we are using the loss function to evaluate the score function. So for example, you remember my space of apples and pears, and it was a two-dimensional feature space where the x dimension was the color measure, which we had greenness to redness. So redness meant negative values and greenness meant positive values between -3 and +3. That was the definition of my space. This is a handcrafted feature, okay? So the y space was another feature. Y-axis was another feature, which was the shape dimension. So I've defined the shape of the apple and pears in a one-dimensional shape vector of ovalness to circleness. So it's like the negative value meant more oval, the positive value meant more circular, and the values bounded between -3 and +3. So if you have this, and if this is your score function, if this is your score function, and if this apple is somewhere in this coordinate space, which I would call it is -1.5 and +1.5, if this is x, then the score function would be this. Okay, so I would say it is this score function. But the ground truth is maybe, I mean, gourmets from all around the world decided that this apple should be 5 in this space, according to the score function. Then you have a difference, 2.5. So this loss function is trying to tell you how good your score function is doing with respect to the ground truth. But it is more complicated than that usually. So how to do it? How to find the correct parameters of the score function so that these numbers will fit each other. That's called training and that's called optimization. But before getting there, I'm going to be talking about different score functions. So this was a regression example. We are trying to find the juiciness value, okay, obtained from these feature spaces. However, when you're doing classification, you need class values. And if you're doing multi-class classification, you need a probability distribution. So saying like, well, this picture is 13% cat, 87% car, and 0% frog. Well, I'd say definitely this score function is not working correctly because calling this picture 87% car is not correct. I mean, the best score function would say this is 100% cat and 0% others. That is what the ground truth was, remember? And for a multi-class classification task, the ground truth was such. And you found the distance between two probability mass distributions, or also called discrete probability distributions. Discrete probability distributions or probability mass probability masses anyways. So cross entropy was a measure, it's a function by the way. If you type it to Wikipedia, you'll come across the formula of it. It is a function which finds the distance between two probability mass functions. Okay, discrete probability distribution functions. Okay, good. So we know the loss function, we know the score function, we know the ground truth. So in supervised learning, what you do is you learn optimization, you do something called the optimization to iteratively change the parameters of the score function so that it will fit the ground truth, and hence the loss function will provide you some low values. There are many methods. In optimization, there are many methods. But in deep learning, nearly all of the methods used to train the networks are some variations of the so-called gradient descent algorithm. Gradient descent we've covered this, as the name implies, finding the gradient in a multidimensional loss space. So this space is like the values in the space are the loss values that you obtain from your loss function. The axes are the parameters of your model, the parameters that you can change. For a deep learning model, these parameters were the weights. So for different weight values, you have thousands of weights in your model, maybe millions of weights sometimes. So this space is a space with millions of dimensions. Hard to visualize. We are human beings, so we cannot. But maybe you can think of it, not visualize it, but maybe dream of it. In that space, you are trying to find the gradients. So it is like finding the slope in a million-dimensional space. And we have vector calculus to do this. Okay, you remember those lessons I was always giving the same example, the blind guy trying to find its way by the feeling of the slope in a multi-dimensional space. I don't know if that exists, but it sounds like a science fiction story to me. Okay, so the training was all about the score function, the ground truth, the loss function, and a strategy, an optimization strategy to find the parameters of the score function such that the output of the score function, the score, will match the ground truth according to the criteria designated by the loss function. Okay, so this was training. How to do it? How to do it in the artificial neural networks? Because this is something very general. This is the general training definition for machine learning. How to do it in deep learning? Before we understand how to do it in deep learning, we should first understand artificial neural networks, and that was what we did. We talked about artificial neural networks, and we learned that the artificial neural networks, the very first definition is a bunch of connection between some input values where these connections are actually some weights. So it is like each connection designated a weight where you use the weight to multiply it with that input vector value. So this is an input vector, you have values of the vector here. And for each connection, you are doing a multiplication. So it's artificial neural networks are multiplication-based models. They are inherited from your, we've talked about this as well, neural system. And in your neural system, you have some neural cells, and in your neural cells, you have axons and dendrites. So these connections are actually correspond to those weights for the electrical system in your brain. So you have these so-called myelin covers in your neural cells. Those covers are sometimes thicker, sometimes they are thinner. And in electrical engineering, some of you will already know that if the cable is thick, then the resistance of the cable will be lower. So it will just provide the electricity with less resistance. So depending on the thickness of your myelin in your myelin covers in your neural cells, those weights changes. So these weights kind of correspond to the thickness of your myelin covers in your neural cells. So that's how it's inherited from the biological neurons. So it's just a simple mathematical model which is inherited, which is inspired by human neural cells. And what you did was not only the multiplication, but summing up all the weighted means multiplied by a weight values, summing them up inside the cell body. If it's a neural cell, we call it the perceptron or a node in a neural network, and apply an actuation function. And we discussed that these actuation functions were nonlinear, so that we could create nonlinear decision surfaces in the multidimensional space that we create, multidimensional feature space that we create for this machine learning task. Those were all the discussions we've covered. So neural networks were comprised of these connections and these perceptrons where you did the weight multiplication, summation, plus the actuation function. Okay, this was something fundamental for any artificial neural network. Most artificial neural network layers did this. I mean, weight multiplication layers did this, but these layers were the heart of any artificial neural network. Okay. Then we talked about computational graphs, because actually computational graph, which is a mathematical structure where you represent mathematical function using graph theory, are actually a common way of representing these neural networks. You have some mathematical function going around here. You can represent them by computational graphs. So for example, consider this very simple function. This very simple function, this function of 3 variables, can be represented with this computational graph. Okay? Why we wanted to represent artificial neural networks with computational graphs was because there is an algorithm called backpropagation, which is a way to implement gradient descent on computational graphs. So the guy who has found backpropagation found it to apply gradient descent on computational graphs. So since neural networks are computational graphs, and since backpropagation is a method to apply gradient descent to computational graphs, so the natural result is we can apply backpropagation to neural networks to train them. And how did we do it? We've covered these, but you remember this. We had 2 steps in training using backpropagation. We first did the forward pass. For an input value, you have fed it to the hidden layers, but you saved the actuation values as well. So at start, the weights and biases were random, initialized randomly. We've talked about initialization as well. I'm going to mention it now. And you have some actuations according to these weight functions. And accordingly, at the end of the forward pass, you have a loss function. You have a loss value. That loss value, the value of that loss is not important. But so it is like the value of that loss is where the blind guy is standing. Is he standing somewhere high or is he standing somewhere low? We don't know. The blind guy is blind. He doesn't know. What he can feel is the slope on his feet. So he follows the slope. Following the slope using backpropagation for this computational graph, we have found the derivative of the loss with respect to these weights. And using the gradient descent, we have updated those weights such that the loss function will decrease. That's the nature of the gradient descent. This for forward pass, backward pass. We did these in batches, so you have 10 input data, you feed them all together, you sum up the accumulate the loss function for those 10 batches, and you accumulate the derivatives for the 10 batches, and you update them. So this was called an iteration. One forward pass, one backward pass for 10 iterations was for 10 mini batches was called an iteration. If you have 1,000 values in your samples in your training set, 1,000 samples in your training set, you'll have to do 100 iterations until you cover the entire training set for the training, which is called and epoch. Okay, and we used gradient descent. Okay then. At this point, we were ready to start the deep learning journey because the deep learning journey started with the convolutional neural networks. Before that, we did not call it deep learning. We called it artificial neural networks or neural networks in a sense. So up to now, what we've talked about was the introductory level of knowledge which prepared you to delve into deep learning. Okay, so we could give a break, but if you have any questions, I'd like to answer them.